Hi guys, I hope you guys are well. In today's discussion, I will talk how to formulate a problem into lamp structure. So specifically, I will talk about calculation of viscosity using wall method. So let's start without any delay. I like to write my script in the Notepad++, but you can write in any IDE you like. So first I will choose the language as Python to just add some colors to the script. First of all, let's write four sections of the script. These are initialization, second one is the system definition, third one is the simulation setting, and the fourth part is the run section. So I will complete these part one by one. So let's start with the initializations section. Here I will describe some variables. The syntax of the variable is variable, name of the variable, style of the variable, and its arguments. So first variable is x. Variable is x and its style is going to be equal. No, its style is going to be equal, and then its arguments are going to be a number which will be 20 here. And next variable is y low and its style is again equal and its value is going to be minus 2.3. Another variable is going to be y high, style same again, and value is going to be plus 23. Let's also define our temperature here. Variable T equal 1 and T is equal to temperature, so that we reminds it so that this line always reminds us that T is not time or something else. In fact, it is temperature. Okay, we can also add variables later on here, so that this section looks like a variable section. But for now, let's move on. Let's define our units here. The problem I am discussing viscosity here is in Lennard-Jones units. So units are going to be LJ. Okay, now I mean LJ. So okay, let's move to the system definition part. In system definition, we can begin with simulation box definition. Okay, let's create a simulation box with the help of create box. But create box requires some regions to be defined first, and this regions needs that a problem should be defined either as two-dimensional or three-dimensional. So let's begin with the dimension command. Dimension, and that's going to be 2. We are working in a two-dimensional. And let's also define lattice. This lattice is going to be SQ2, which is square, and the lattice parameter is going to be 0.6, and style of the particles will be atomic. Okay, Okay, now just define a region. Syntax of the region command is region id of the region, style, arguments, keyword, and the follow-up arguments. In the particular case, this style is going to be block. So let's first name our region, and that is going to be simulation box region, and I'm just writing a simulation box, and the style is block. And let's pass some arguments related to the block, and that is going to be x, starting x, ending x. It means we need to define the x direction, y direction, and its ending y. And we know that this is a two-dimensional problem, but just to satisfy lamps we provide z direction with a very little value, and that is 0.1 dimension, 1 value. We have not defined our x low and y low, so I like to write here 0, and x is going to be x variable. And way of writing a variable in lamps is using the dollar sign, and same for the y low. But for a variable named with more than one character, we need to mention the curly brackets around the variable. That's how the lamp style works for variable with more than one character. Okay, using this region we can now define our simulation box next. So let's define our simulation box with the help of create box command. Syntax of the create box command is create box command, n region id, keyword, and value. So n means here the type of atoms. So here we will use 3 type of items, and the region id is going to be simulation box, right? And there are no specific keyword and values to pass on right now. Okay, let's also define the mass of the atoms. Before defining the mass, we also need to create atom first, right? Create atoms, and we are going to create atoms 1 of type 1 with box. Okay, now we can define the mass command. For all atoms we are going to assign a mass of 1. Star means that all atoms considered here have the mass of 1. Okay, next command is neighbor, neigh per modify. This tells the frequency of neighbor list rebuild, and we define it as delay 0 every 1, means build the neighbor list after every time step. That is going to be computationally expensive but more accurate. Anyhow, okay, let's move on and now define the simulation setting. For the simulation settings, we are mostly concerned with the regions, groups, setting some velocities, giving some velocities to the atoms, and defining force fields. So let's move to the region. How to define regions in lammps. Syntax for a region command is region, and the next is ID of the region and its style, obviously style, and its arguments and keywords. We have already defined the region above, the simulation box region with the box style, but here we decompose the above region into various sections. First we define the upper region. Upper region is with the name upper and the style block, and we then pass the keywords. Previously we defined keywords as extraction values, starting and ending value for the x, starting and ending for the y, and starting and ending for the z. Same here, we define our region as extraction, starting and x, starting x it is going to be inf, ending x it is going to be inf, and the starting y is going to be something different, and ending y is going to be inf, starting z is inf, and the ending z is inf. Okay, block style takes various arguments, and these are the tractions of the dimensions, and their values can be just numbers, which I have defined for the simulation box. For the extraction I have used 0, and this is an example of just using a number. You define a starting number and an ending number, it defines your extraction for that region. And second option is edge, which means use the current value of the simulation box for this region, but I am using inf, which means use a large positive or negative number. This means that a very large number will be assigned to the starting direction of the x right here, and also to the ending direction of the x, but for the y direction it is not the case. For the y direction this number is going to be some value which we have not defined, of course, and I will define it here. Variable y equal is going to be 20. Okay, this upper region starts from the 20 and extends to the boundary of the simulation box, and same goes for the z direction. So what's the difference between edge and inf? The difference between edge and inf is that when simulation box changes size, the region does not change for the case of edge, but for inf it is already large enough to encompass the simulation box. Mean it is already large enough. Its simulation box changes to another value, the region is already there, because the region value in that direction is already large enough. So let's define also another region, that is going to be lower region. Lower region is also going to be of block style, yes, block style, and the starting direction for the x is going to be inf, and the starting direction for the y is going to be inf, and the ending direction is going to be something of value, and that is 0. Inf. That says that start from the simulation boundary and wherever it goes and end at the position of 0. So we have already defined our region of simulation box here as the starting direction of y as -20, minus 2.3 and the ending direction as 23. So starting from the simulation boundary, which is minus 20 minus 2.3 and ends at the 20, this represent the lower region of the simulation box, and the mid region is going to be some other region which we will define next. But now move on and define some groups in the simulation box. So how to define groups in LAMMPS? The syntax of the group command is group ID of the group, style and argument. So let's start with the command name and just name it the upper group, because this group going to contains the upper region. So ID of the region that it's going to be contain is, let's first tell region and upper. So we have defined a group name upper that contains the region name called name upper. Now also define the lower region, lower group, which will contain the region lower. So that's how you define the groups. Now what is the purpose of grouping? The purpose is that we want to define a wall. Upper and lower groups are going to be the walls of the simulation box that will not move during the simulation. Moving means not that they are moving means that our main calculations will be calculated in the middle part of the simulation box, because we are going to give this part of the simulation box some velocity and we will call it flow. But for now let's make another group name wall and use the style union, and what we are going to union is upper group and lower group. So now we have a group name wall, which is the upper region and lower region we have just defined. Okay, now it's time that we define the flow group. Flow group is going to be something, not a wall, and that is going to flow, and that's where we will calculate our viscosity. And how we can describe a group named flow? We are calling it flow group. So just subtract the wall all from everything we subtract the wall. What we get is the group name flow. That's how the things are working here. Okay, now let's move on and also allow the atoms to have some velocity with the help of some velocity command. Velocity command can be used to give atoms some velocity, and the syntax is velocity. You give some which group you want to give some velocity is so you mention its ID here, and you mention the style of the velocity, its arguments and values. So the velocity can be given to the flow group and also to the one wall, because we are using wall method, and for to apply shearing we need to one wall of the simulation box. So let's first give the velocity to the flow group. Okay, to which group we are going to give velocity? It is flow. And what is the style we create? And temperature is going to be 1, and we need to pass some random seed, and that is really random. 29287 97287. Okay, let's give some velocity and also give velocity to the wall, upper wall, and that group is upper, and set the velocity equal to 2.7, which is the shear rate, and other dimensions are going to be 0 and the units are going to be of box. So that's how we define we give the velocity to the flow group and the upper wall group. Okay guys, before moving to the run section, let's end our video here and meet in the second part of the discussion. Okay guys, see you in the next discussion.